Assalamu alaikum to everyone. Welcome to second PSU Prince Sultan Memorial Distinguished Research Lecture Series. I'd like to introduce our honorable guest. I don't know how to put your achievement in introductory short comment, but Professor Luciano is a full professor in University of Salerno. He received his bachelor and master's from University of Salerno and PhD in structural engineering from the University of Naples, Federico II in Italy. He participated as a peon or co-principal investigator in various research projects funded by the Italian Ministry of University Research, the Laboratories University Network of Scientists Engineering. He is author of 280 plus articles in impact factor rated scientific journals. He is also the editor of Europe of Composite Part B Engineering, a severe publisher, one of the leading journals in his field. He is also the board of editorial members of various international journals, including our PSU Research Review. Let's welcome Professor Luciano Feo for the distinguished lecture. Thank you.
First of all, I want to thank, we say, Magnifico Rettore, for inviting me to, for this visiting your university. I am honored to be here, and I really hope that this can be the first step of our future collaboration. And of course, let me thank my friend Dr. Nurabi, because he's taking care of me in everything. First, I would like to show you two movies. One is of my city, and the second is of my university, so that you can a short presentation of my university.
The geographical position of the University of Salerno makes it the ideal location for a campus university, as it is within easy reach of both Salerno and Avellino and the relative motorway exits. It is a campus which is in constant evolution. More teaching rooms and research laboratories have recently been added to the existing ones. Today, we have 208 lecture rooms, a total of 17,802 seats, and research laboratories which are spread out throughout the campus for a total area of 22,000 square metres. Surrounded by gardens and landscaped squares for a total area of 258,000 square metres. As environmentally friendly as possible, and so use solar panels, solar cooling systems, photovoltaic and cogeneration methods to save energy, and we are currently producing 30% of our total energy needs. Our university residencies are modern and provide everything that students could need. We currently have 628 beds available for students and teaching staff, and another 152 are currently being built. The university canteen can seat up to 1,300 people, and it makes around 3,000 meals a day. To make life on campus as pleasant as possible, we offer various sporting facilities: an indoor swimming pool, 3 5-a-side football pitches in AstroTurf, a tennis court, 2 multifunction courts, a climbing wall, a cycle path, and a 1,200 square metre gym where it's possible to play basketball, volleyball, table tennis, do gag and tone, step, total body workout, etc. The main university library, the Caianello Library, was inaugurated in 1997 and is home to publications relating to the humanities, law, economics, technology and pharmacy faculties. It can seat up to 600 students and has 18 different consulting rooms. A new scientific library was inaugurated in 2003. This facility can house up to 400,000 books and materials, such as those which were previously housed in the library belonging to the Faculty of Mathematics, Physics, Engineering and Pharmacy. This office enables students to make the most suitable choices regarding their course. It also offers advice and support during their degree, as well as helping and advising new graduates approach the world of work. The office has an information point which is open all year round. The Erasmus Office is responsible for exchange students and teaching staff coming to study at the University of Salerno, as well as placing our own students and teaching staff in other European universities. It is also responsible for collaboration with institutions and research centres in Europe and beyond. Our nursery can accept up to 60 children from the ages of 3 months to 3 years. It is open to the children of university staff, students and residents of Luciano. The university has its own radio station whose aim is to instruct, inform and entertain. It also videotapes conferences, seminars and lessons and also publishes these online. The University of Salerno was the first university in Italy to develop its own TV company. There are 60 monitors, each 46 inches, and a video wall informing students and staff of what is happening on campus. Students don't just come to the University of Salerno to study, they come to experience different situations in different contexts.
Second presentation. So as you know, the title of the presentation is Composite Material Infrastructure, State of the Art and Modern Code Development. The presentation is divided into 4 parts. In the first part, I will give you the definition, the basic concept, terminology, constitutive law, and some manufacturing technique of composite material. In the second part, I will talk about the advanced composite as strengthening materials for civil construction. In the third part, I will talk about the wool composite structures realized with the FRP pultruded profile. And the last part is dedicated to the result of my research on a very specific problem related to the statical behavior of this profile. So let's start with part 1 of this presentation, with the definition of composite materials. As you know, a composite materials is a material made from 2 or more phases with the aim of produce a new material with physical, chemical and mechanical property greater than those of the individual component. Typical example of conventional composite materials are of course masonry and reinforced concrete strengthened with civil parts. Fiber reinforced polymer, also called FRP, is a composite material made of a polymeric matrix reinforced with a short or long fiber. This special class of composite materials present many advantages over conventional materials such as high strength, high stiffness, low weight and also good corrosion resistance. The most commonly used fiber in FRP are carbon fiber, so we say CFRP, glass fiber, glass FRP, aramid, with the most widespread polymeric matrices being epoxy resin, vinyl ester and phenolic resin. This table shows a comparison of the physical and mechanical property of the fiber and polymeric matrix in relation to steel. We have typically 2 classes of glass fiber, E-glass and S-glass, with different value of Young modulus and tensile strength. 2 classes of carbon fiber, high modulus and high strength, aramidic, and of course polymeric matrix. Glass fiber typically have a Young modulus of elasticity lower than carbon and aramid fibers. In addition, they are prone to creep and are characterized by a low Fadic strength. Carbon fiber are used for their high performance and have high Young modulus of elasticity and also a high strength. Aramid fiber are organic fiber and their modulus of elasticity and also the strength are intermediate between glass and carbon fiber. The most commonly matrices for production of FRP are thermoset resin. The advantages of this resin are the low viscosity, good adhesive property, good resistance to chemical agent, and also absence of melting temperature. The disadvantages are limited range of operating temperatures, poor toughness with respect to fractures, and also sensitive to moisture during the application. The most common thermoset resin used for civil application are epoxy resin, polyester resin, and vinyl ester resin. The epoxy resin is characterized by good resistance to moisture, chemical agent, and have excellent adhesive property. In order to understand the mechanical behavior of composite materials, it's very important to give some definition and defining characteristic of FRP. which are the geometry, so the shape and dimension, the fiber orientation, it means the orientation of the fiber with respect to the symmetry axis of the materials, and also the fiber concentration, volume fraction, distribution, dispersion, and so on. Generally, composites are made of thin sheet, known as lamine, or layer or plies, which are bonded together in order to form a laminate. A lamina may have either unidirectional or bidirectional fibers embedded in the matrix. And a lamina containing woven or braided fiber is referred to as a fabric. So this is, typical unidirectional lamina, bidirection, and a fabric. The mechanical behavior of composite laminate depend on the property of the fiber, the property of the matrix, of course, and the amount and the orientation of the fiber in the matrix. Another important definition is this. In fact, the adjacent lamina realized with the same fiber and having the same orientation are referred to as a ply group, which can be treated as one layer. In order to analyze the mechanical behavior, we generally introduce a reference system, X, Y, and zeta, orthogonal to the plane of the laminate. And the orientation of the unidirectional layers in the laminate is specified by an angle theta. So this is theta is equal to 0, 45, 19 degree, and generic value of the angle. The number of ply within a ply group is specified by a code that we call Laminate Code. For example, this Laminate Code refers to a composite made of 4 ply group. The first group contains 3 ply of the same thickness in the 30-degree direction. The second contains 4 ply in the 45-degree direction. The third 2 ply in the 60-degree direction, and the last one only 1 ply in the 90-degree direction. Other important definition and terminology that can help to understand the composition of composite materials are the following. If all the layers have the same thickness, the laminate is called regular. A laminate is also said balanced if for every ply in the plus direction there is an identical ply in the minus theta direction. Moreover, a laminate is symmetric if layers of the same material, thickness, and orientation are symmetrically located with respect to its middle surface. Moreover, in a cross-ply laminate, fibers are only in the 0 and in 90-degree direction. And finally, an angle ply laminate consists of a ply in plus theta and minus theta direction. Just a few words on the Constitutive Law that is very important for the understanding of the engineering behavior of these materials. As you know, due to the intrinsic constitution and for a microscopic point of view, these materials are anisotropic and inhomogeneous material. However, from a microscopic point of view, it is possible to consider these materials as linear elastic orthotropic material up to failure and also elastically homogeneous. Their constitutive law is given by this relation, which is the well-known generalized Hooke law, where T is the Cauchy tensor or stress tensor, E is the strain tensor, and C is the stiffness tensor. In terms of component, the constitutive laws can be, is given by this equation, where the Cartesian component, also called elastic constant of the composite materials, for an anisotropic material are 81. As it is also well known for the symmetry of the two metrics, T and E, the number of elastic constant reduces to 36, and then if we also introduce the hypothesis of hyperelasticity, the elastic constant are reduced to 21. Moreover, particular symmetry property may introduce further simplification in the constitutive law, resulting in further reduction in the number of independent elastic constants. The main and most significant cases of symmetry are monoclinic material, orthotropic, transversely isotropic material, and isotropic materials. These are some slides. I will go very fast here. In any case, these are the constitutive relation between the strength and the strain for all these 5 kind of symmetry. Very important is the technology of production of these materials. The most common is the pultrusion, which is based on a continuous manufacturing process consisting of 3 main phases: forming, impregnation, and hardening. As you can see, the fiber are taken directly from the rolling and conveyed to a raising tank for impregnation here. Then bundle of impregnated fiber enter in the heated die, where the material is formed and cross-linked under high pressure. At the end of the process, the material is cut to length. So with this process can be produced many shape of beam for non-load bearing, but also for structural application. We call this steel-like pultruded profile. Let's see now the second part, which will give you an idea of the application of this material. So the topic of the second part is the use of composite materials as strengthening materials for existing structures. In the last few years, in fact, the use of composite material to strengthen or retrofit existing structures is becoming more and more frequent in the field of civil engineering. As you know, the traditional technique for extending the useful life of structurally deficient or functionally obsolete structures uses steel plate, which are externally bonded to existing structures. For example, these are 2 reinforced concrete structures strengthened with the steel plate on the external surface or on the lateral surface. Nevertheless, the use of steel plate gave rise to many shortcomings, such as high installation cost and weight, visual intrusion, and of course, possibility of corrosion. Nowadays, all these drawbacks can be easily overcome by applying advanced FRP composite materials. The interest in this technique is widespread and is continuing to grow due to the ease of installation, the high strength-to-weight ratio, the lower maintenance cost, and also the higher corrosion resistance of these materials. In Italy, research on this topic started at the end of the 19th, and in the less than 20 years, it has become one of the most active and prolific research fields. In fact, in the last 3 years, more than 20 inter-university research projects have been funded by the Italian Ministry of Scientific Research, and more than 20 different universities nationwide collaborate on a regular basis on most diverse FRP-related topics. I'll show you some result of this project. In particular, we have started by studying the mechanical behavior of a strengthened beam, which can be seen as the combination of a concrete core and of a composite overlay, which can be externally bonded on the surface. This is very important, this mechanical model, to understand the response of the beam. Due to the high stress concentration at the end of the plate, imagine this is the reinforced concrete beam, and this is an FRP plate bonded with a matrix at the lower surface. And in this section, there is a high concentration of stress. And this can produce, as you see, the bonding of the plate with the total separation of the composite from the concrete beam. So in order to validate our mechanical model, we have performed and developed many experimental tests in our lab. And as you can see, in order to measure the strain into the concrete and also on the surface, we have used strain gauges, electric strain gauges. These are some phases of the preparation of the beam, and here's the final result. These are beams strengthened inflection with different percentage of and length of the external plate, and this is the instrumentation of the beam before test. These are some results of the failure of the strengthened beam. We also have developed many research on the application of composite material on existing masonry structures in our lab. This is, for example, application of carbon fabrics on a masonry vault. As you can see, these are carbon applied to the top surface of the vault. These are arches, and this is the failure of the structures. We also use this material to strengthen masonry walls, and the problem is, of course, the same of the concrete. In fact, there is a debonding of the FRP from the surface, external surface. And this is another application in earthquake problem. In fact, you can see a lateral force which simulates the earthquake, and this is the result of the experiment. We have also developed many research on the application of FRP in timber structures. We use, for example, internal carbon rebars to strengthen timber beam, or external plate. Also, other universities are studying the strengthening of metallic structures with fiber reinforced polymer in many universities in Italy. So now it is a common feeling that Italy is getting a worldwide reputation, both for the value of its scientific contribution in improving the knowledge in this in this field, as well as for the presence of a peculiar and important building heritage. And these, of course, include those of historical and architectural relevance, as well as more recent masonry structures, reinforced timber and metallic structures. Most of these structures are now 50 years old and in need of urgent structural remedial works. The main international guideline for the identification of the behavior of this material are the Japanese one, recommendation for design and construction of concrete structures, the American ACI 414 guide for the design of and construction of externally bonded FRP system, and the European FIB related only to the external bonded FRP reinforcement for reinforced concrete structures. Recently, the Italian National Research Council has promoted a special initiative of experts from university, of course, involved in research activity on FRP. And after less than 3 years of working activity, we have developed a series of technical documents on the use of the FRP materials for strengthening of existing structures. These documents are the so-called CNRDT 200, related to the guide for the design and construction of externally bonded FRP system for strengthening of existing structures. In this case, we have materials, reinforced concrete structures, pre-stressed RC structures, masonry structures. Then we have another document, very important, this is document 201, related on the timber structures, and the 222 document on the metallic structures. The content of the first document are the following. We have materials, basic concept, strengthening of reinforced concrete structures, and the strengthening of masonry structures. Of course, a specific guideline for the strengthening of civil construction subjected to earthquake are also provided in this document. It is widely recognized that the design of a FRP system is a critical process, and the components have different mechanical property and rule, and for this reason must be selected and designed to work together in a single system. It is also said that the design of the FRP strengthening intervention must meet with the following requirements: strength, serviceability, and also durability. Some application in Italy. This was a very important building in Napoli. It was hit by a fire at the end of 19 here, and it was strengthened by applying carbon fiber on the wall, the seismic wall. Also, the beam were reinforced both in flexion and also in shear, as you can see. Also the pillar, the column of the building. This is another application for a bridge hit by a truck, and it was also strengthened and restored by with the application of FRP materials. As you can see, it's very, very easy to apply these materials to the external surface of the beam. Other applications are the confinement of pillars, of bridge pillars, for seismic increase of the strengthening. Also, some application in masonry structures. Why we use carbon fiber or glass fiber in masonry? To increase of course, of strength. The strength in walls, arches, or board. For the confinement of pillar, for the transformation of a non-structural element into structural element, for the stiffening of horizontal slab, and sometimes for the introduction of tie in the so-called tie in the building at floor and roof level. Some application in Italy. This is a very old palace in Piacenza, and as you can see, the top surface of the vault was reinforced by using carbon fiber. This is Venice, very famous city in Italy, and this is a bridge which was also reinforced with fabric of carbon materials, as you can see in this slide. This is another very famous church, is Urbino Church, and also in this case the arch of the church were reinforced by using FRP. This is a masonry bridge in Sangro, the so-called Sangro River, and also this structures was reinforced by using carbon fiber materials. As this other document on the strengthening of existing timber structures, this of course with various kind of application, and we can say that timber beam can be strengthened for two reasons. One is the increase of load, and another important is the reduction of the resistant sections following illness, such as fungal attack, insect attack, or other traumatic events such as the fire. In this case, we can apply protruded profile or internal rebar or external lamina at the surface of the timber beam. Finally, we have some application of this technique to real cases. This is a Siaz building in Trevi, where you can see that these materials have been applied at the surface, external surface of the beam. And finally, we have the application on metallic structures. This is another bridge in Venice called the Corona Bridge, and some application in Europe, in England, with this kind of materials. Finally, in Italy, we have also developed three other documents on the use of FRP bars, on the use of fiber reinforced concrete, and finally on the design and construction of structures made entirely of FRP protruded element. These documents are in English, and of course you can find in the website if you want to look and to read the document. Now I will talk on wool composite structures. With giving some example and a guideline in Europe. Historically, of the shape protruded fiber reinforced polymer were developed, as you have seen, and designed by the protrusion industry and were intended for low stress application. Recently, these materials have been introduced as primary structural member to replace or complement other conventional materials such as steel, concrete, and wood in critical applications such as bridge decks, pedestrian bridge, and also recently in highway bridges and other infrastructural systems. These solutions are often imposed in Europe by specific needs, such as requirement for speed of assembly on site, enhanced resistance to aggressive environment, and also lightweight of the FRP composite materials. The main benefit associated with the use of FRP in civil construction are better opportunity for precasting, reduced traffic downtime during assembly and the launch of the structures, reduced risk for accident associated with on-site work, of course reduced manpower costs, competitive prices over the structures like sickle, high quality of the structures, freedom in shape, and also easy transportation of component to area hit by a natural disaster. Let's see some relevant example of civil engineering structure realized in Europe with the use of FRP. So here we have two bridges, one in Denmark. The first one is a pedestrian and cycle bridge made from 100% of protruded profile, glass fiber profile. The bridge is 40 meters long, and its total weight is only 120 kilonewton. Another pedestrian and cycle bridge is in North Habi, and the bridge is 23 meters long. Other applications in France are a solar charging station, which is a structure made to more than 80% of its weight in composite materials, and also a helipad made by protruded glass fiber profile. Other application in Germany or in Italy, this is for example very important, is Santa Maria Paganica Church, L'Aquila, for the replacing of the roof of the church, which was damaged by the earthquake of L'Aquila in 2009. Other application in the Netherlands, and maybe this is one of the most famous in England, is the Aberfield Bridge, which is more than 100 meters long, and has a main span of 63 meters. Also the two piers and the deck are made of glass fiber reinforced polymer, while the stay are made of aramid fiber cable. Only the foundation and are made of concrete, and the steel connection between the stay and the pedestrian walkway. This is another bridge. Also in Russia, there are some application of a bridge completely made of protruded member. In Iceland and in Spain, and also in Switzerland. This is a very famous building. This is the so-called A-catch building made of glass fiber protruded beam. Consists of 5 floors with a total of 15 meters high. And maybe this is the last realization that I'm showing you, is a pedestrian hybrid footbridge in Portugal. Notwithstanding all the opportunity offered by FRP composite, it appeared necessary with the standardization work also in Europe for both the production of FRP structural element and the practical rule for the design and verification of structure entirely made of this element. Several countries have already contributed to the drawing up of appropriate guideline, and for example we have some guideline from Sweden, from Germany, from Italy of course, and from England. The experience so far gained through the realization of FRP composite structures in many European and also in non-European countries, as well as the theoretical and the experimental knowledge gained in this field, make now possible to develop a guideline to be shared within the European country and also the non-European country. And to achieve this outcome, the European Committee for Standardization has recently published a scientific and technical report drawn up by the Working Group number 4. The name of this scientific report is Fiber Reinforced Polymer Structures. And this report includes all the predictive rules which can be considered as the most up-to-date and reliable for the design and execution of all FRP composite structure in the world. This is the document, and I have contributed to this document for the chapter of the joint. That is a very crucial and very important aspect. Of course, also this document can be found in the internet, and if I can send you a copy if you need this report. Finally, I will give some idea of what is my current. What are my current research on this application? In fact, in the last part of my presentation, I will present the result of an experimental and numerical investigation on a very important aspect, which is the axial and rotational flexibility of the junction between the web and the flange of these materials. In fact, a highly complex and delicate aspect, unique to steel-like unidirectional protruded profile, is associated with the strength and the stiffness of the junction between the web and the flange. In fact, the insufficient fiber continuity in this junction may lead to progressive degradation of both the axial and rotational stiffness, affecting the buckling, post-buckling, and of the overall short and long-term structural integrity of the profile. This is a very important feature because this is a bolted joint. And as you can see, there is a separation between the web and the flange due to the insufficient fiber continuity in the profile. But the connection is safe. In fact, the mechanical property of the junction are not the same as those of the web and the flange, due to the fact that this portion of the profile is, as we say, resin rich. Because in this part, in this junction, this web flange junction, there is more resin than fiber. So this is very critical point for the design of these structures. For this reason, we have developed a joint research program between the University of Salerno and the University of California, Irvine, with the Professor Sultan on this topic, with the main aim of develop the relation between the displacement and the load, and also between the moment and the rotation, that are necessary to predict the local and global response of these structures. The experimental program consists of two phases. The first phase was carried out at the University of Salerno, the second at the University of California, Irvine. In the first phase, we have evaluated the axial behavior of protruded high profile, while in the second part of the first phase, we have evaluated the influence of the pull-out load location on both these two problems, the stiffness and the strength of the junction. During the second phase carried out at the University of California, Irvine, we have investigated on both the axial behavior of H profile and also on the rotational behavior of web flange junction. These are some detail of the geometrical characteristic of the profile that we have investigated. These are the nominal values that were supplied by the manufacturer, but we have also verified the mechanical characteristic in our lab. These are the name of the profile with their geometrical characteristic, and their geometrical characteristics are also reported in this table with the nominal values of the mechanical property. For the pull-out test, this is very important, we have developed two different tests. One is the so-called endpoint test setup, and the other is the midpoint. In the endpoint test setup, the pull force was applied at the end of the spaces, as you can see, here and here. While in the midpoint, the pull force was applied at the midpoint of the spaceman. The first test setup simulates the typical failure of an open web protruded column at the beam column framing connection, while the midpoint test setup simulates cases of local buckling of the beam or of a coupling. This is the setup of the experiment in the University of California, Irvine. Some result of the investigation. And this is, sorry, should be a movie. Okay. So this is what happened. This is the load is applied by this steel, and so as you can see, it's very, very. The resistance is very, very low, and there is the total separation between the web and the flange in the junction due to the less concentration of the fiber. Of course, we have obtained low displacement curve and also failure mode for all the beam that we have investigated, with some conclusion that, for example, the value of the failure load obtained from the endpoint pull-out test were about 1/3 smaller than those obtained from the midpoint test. We have also developed second part of the research with the aim of investigating the influence of the location of the force from the edge of the spaceman on the strength of the junction, using different length of the profile. And we have also developed the experiment, and we have obtained for all this beam the low displacement curve and also the failure mode. And we have also some important conclusion on this part of the research. In order to validate the mechanical model that we have performed and also the experimental investigation, we have made some comparison with the numerical result of a finite element model that we have performed using commercial software. These are typical finite element model for the endpoint configuration and for the midpoint configuration. and these are typical stress distribution at the Weber-Flange junction. As you can see, the red color means that there are high stress concentration in these parts of the beam. And of course, in order to compare numerical and experimental results, we have used strain gauges to measure the strain and the displacement, and we have also compared the numerical and the experimental result with the numerical result. And we find a very good agreement with the two results. Finally, we have also used a new technique which is called digital image correlation in order to capture the displacement and the strain in a plane. Digital image correlation is an innovative non-contact optical technique for measuring strain and displacement, and it works by comparing digital photograph of a specimen at a different stage of the deformation. This is a view of the instrumentation and of the preparation of the surface for this specific application, and these are typical and longitudinal and transversal displacement map. As you can see, the violet color showed the part of the beam with the higher displacement and strain with respect to the other part of the beam, also in the transversal section. Finally, we have developed another important experimental investigation on the rotational behavior of this beam, because we can have two different kind of behavior: opening connection, opening mood, and closing mood. And the behavior is totally different, as we have seen in our experiment. And these are the results of our experiment. And in conclusion, we have developed a research on the axial and rotational behavior of this special junction in protruded composite profile. And this study highlighted the importance of the junction strength and stiffness and its influence on the overall structural behavior of PFRP structures. And for this reason, it is now necessary to take into account the result of the proposed research when developing standard tests to provide the designer with the necessary strength and stiffness information that will establish the design beam state for protruded composite structures. Before, of course, we have published the result of this journal research in two papers recently published by Composite and Elsevier, and this was a problem that the industry did not say to the world of it is scientific and also for technical, and it was very, very important to develop this research. And now we are continuing to develop this research, and I hope we can also develop this research with your university if you are interested. Thank you very much, and I hope.
Okay, thank you very much for your very technical, of course, presentations. If I just may ask, maybe it's technical, also a question. You're talking about now the failure between the web and the flange in an IV. And it depends where the location, what it is, at the center of the beam or near the support of the beam. Now, what would you classify the failure? Is it a shear failure or a bending failure, or what? Is it torsion failure? Because now, since the flanges mainly to resist the bending, and the web more like shear. So where is the exactly that I can identify as behavior where the failure occurred? Or using, I mean, and the fabric, you said you could use just stiffeners for the flanges.
I think that this first idea is the shape is not good, because when we use metallic structures, of course the I-beam is the most important shape, and the industry of the protrusion produce still-like protruded profile, still-like. But in my opinion, this is not a good shape. We try to strengthen the junction between the web and the flange with the C angle or with stiffener. But my idea is that we have to change the shape. Yeah. So because the separation between the flange and the junction is very, very sudden, premature, and as you have seen, it can occur in a failure of the structures, even if the connection, the bolt connection, continues to work. So my idea is to suggest to have a channel or closed shape for the application of this kind of pneumatics in the civil construction for structural and load and high load application. I don't know if reply to your.
No, but I'm just saying, what can we identify the failure as? What is it? Is it a shear failure, or is it when the tear happens between the flange and the web?
Okay. I can show the one. I want to show you this again. Sorry, just one moment, because this is very important. Okay. So, if you look at this picture, the fiber are along the beam axis. So, in the transversal direction, you don't have fiber.
So that's near the support, right?
This
the location of the
location is not near, but is in the midpoint. But this is not the problem. Is that the fiber are on this direction, longitudinal direction. In this direction, you don't have any fiber, so you only have matrix. And of course, this is the weak point of the connection, as you can see. Fiber are in orthogonal to the beam, and here you only have bracing. And so this is the also here. So,
Okay, thank you. Anyway, I'm sorry. But now you are loading the beam as a bending, right?
yes,
Just regular loading in the middle.
bending, yes, of course.
Thank you. My last question, when you're talking about composites, you're talking about the three options, using polymers or using glass, the two materials, or using the third one? Huh? Carbon, yes. Okay, when I use carbon, what happens to because carbon ductility will be more, ductile material. But when you use polymers, it's more like elastic. So do you have like stress strain diagram for each of those? So I know where.
The problem, okay, thank you. Of course, in composite materials, for the strengthening of the existing structures, as well as for new construction, the problem is the interface and also the phases. So we have two different behavior of course, of the resin and of the fiber. But and also this behavior, we have to be careful also in the long-term behavior, because maybe there is a problem of creep, and this may affect also the overall behavior of the structures. Concerning your question, I have to say that if the loads are not very, very high, there is no problem between the two different behavior of the resin and of the fiber. In civil engineering, of course, application.
Professor.
Thank you.
Professor Feo, Luciano, up here. Thank you again for your informative lecture. We have a first question from the women's campus.
Thank you for your lecture. My name is Suki Yun from Architecture Department. I have a simple question about this new material. Is there any fire resistance test on this material? And then the second question will be, is there any test of the under extreme weather condition, like coldness and then hot weather like here? And then
this is a very weak point, because no fire resistance for this, no fire resistance for these materials. So if you want to use, you have to protect them with special films. And also we have performed some research. In particular, I am working with Professor Mizifan from Brunel University on aerogel materials, which can be like a thin film on the surface of the element and can give a fire resistance. But at the moment, it is a very weak point for this application, because I can say that after a temperature of 70, 80 degrees, the so-called transition temperature, last transition temperature, there is no resistance of this element.
the second question was about this building performance level in extreme weather condition. Is there any research done on the subject?
Not my university, but we are performing some research on the long-term behavior. This is 5 years research, and we are going to finish and complete this research and to publish the result of this research. Thank you.
Thank you for your presentation. My name is Sultan. I'd like to ask about the finite element software. Which software you use for this research?
We use different software. Of course, we have made software by ourselves with a discretization of Hermite element or Lagrangian or Hermite element. But in this case, we use the Strauss. It was a nonlinear finite element model. It is very important because the different part of the pursued elements have been modeled with different elements. In particular, the core has been modeled with brick elements, while the mat, the glass mat, the external surface of the beam has been modeled with two-dimensional model. And also we have also used abacus, but we have found the same result. So every software that has the possibility to change the property and to take into account that the material that you are studying is orthotropic materials, so you have to give at least five elastic constant you can use to develop and to obtain the result.
Do you think abacus is good for modeling composite structure?
Yes, of course. Also in nonlinear cases,
Yeah.
it's very and also for geometrical nonlinearity and also for mechanical nonlinearity.
In my PhD, I did the same, the mechanical and experimental. I used the abacus for mechanical, for modeling steel fiber reinforced concrete.
Okay. Thank you.
Thank you so much.
Thank you.
Dr. Feo, here.
Oh,
Thank you very much for this nice presentation. I have some question here. In the protrusion, there is an inherent problem, which is unidirectional fibers, while in application you have, the both longitudinal and transverse loading. So there is an inherent problem with the transverse loading. I think this is what causes this failure. Using the laminate structure, you can have different stacking sequence, and then you can avoid such by loading. How do you plan to overcome such a problem?
I totally agree with you. In fact, I started to do this research not because I fall in love with composite protrusion, but just to say to those persons who use these materials and this protrusion that there is a problem. The problem is this one, that the protrusion elements are very strong in one direction and very weak in the other direction. But nobody knows this because in Italy and in other countries they start to use without taking into account of this problem. So we start to show that this is not a good shape, not a good materials for structural application, for some structural application. And so we will suggest, of course, a laminate beam or a different manufacturing process to obtain a beam with almost the same characteristic in terms of strength and stiffness in all the directions. But of course, orthotropic materials is not isotropic materials. So you have to consider and to live with this difference. This may be seen as a disadvantage, but if you have only one direction of stress, you can perform a very good materials in that direction. So for the first time, using composite materials, we can say that we design not only the structures, but we design the materials. And this is the very important topic, the very important aspect with the use of these materials.
Okay.
In Italy, yes, in Italy, we are using a lot of composite materials for the strengthening of reinforced concrete structures, in particular for after earthquake, and there is a huge number of applications, and this is maybe the main, the most important field where this material can be applied at the moment. I believe that we have to think to other manufacturing process in order to have the best from these materials. Maybe 3D printing with the fiber embedded and can be the best solution. But what we want to show is this: if you use the protruded beam in case of bending application, you will have this problem. And this is a problem that was not reported in any guideline, national, European, and also non-European. And so the designer did not know this problem, and this can, of course, be a very, very important problem for the engineering, civil engineering construction.
Okay, we have a question from the chair of our architecture department, Dr. Bethena Leonti.
What about the economic feasibility? What is the cost difference between the FRP and FRP and typical RC?
Now I can say that the total cost is the same. When I say total cost, I mean the initial cost of the product and the maintenance cost, because the hyper-corrosion resistance result in very low and very cheap intervention with respect to the restoration of the materials. So in Italy we have a big steel industry. So the problem is the industry don't want that these materials and the application of growth, because the Italian economy is also based on steel. So this is another problem. It's not a technical problem, but of course I can say that in a long period, the cost of an application of FRP in relation to conventional materials is almost the same. Almost the same.
Thank you for your presentation. I have a question regarding the seismic application. If you consider the FRP in strengthening or retrofitting, considering the low ductility of the fibers compared to, for example, to steel, so how reliable FRP, using the FRP in strengthening, considering the seismic applications?
There is a lot of application of FRP, especially in the joint between the column and the beam. We resolve this very important problem with the so-called hierarchic resistance. because when we design the structure, we impose some restriction, and then we can give a utility to the joint, even if the materials doesn't have this utility. So we impose some restriction in the performance of the materials in order to have quasi, as we say, ductile behavior of the joints. But of course, I want to show you another slide. There is a breakthrough failure. In fact, when we start to develop research on this application, in particular on the application of FRP for the rehabilitation of a reinforced concrete structure, we noticed the bonding of the plate, carbon plate, from the external surface. This is due to high stress concentration. Starting from that result, we have studied some stiffener, some application that can help the strength of the final of the end of the plate. So there are some specific guidelines that can help you or a designer to fix this problem. But of course, also there are the limitations in the percentage of strength that you can give. You cannot go over 50% of the strength. So if you can make safe structures, improving the strength of less than 50% is okay. In case you cannot use FRP. Also because due to the creep behavior, we don't know what will happen after 30 years, 40 years, to the interface between the plate and the concrete cover. So this is an open question, and for this reason we are continuing to study, in particular, the creep behavior of this application.
Yes. Good question regarding the finite element model. How did you model the FRB as elastic material or inelastic material in the finite element?
We develop as transversely isotropic material with 5 different constants. In particular, you have 2 elastic Young modulus, one in the longitudinal axis and the other in the transversal direction. You have 2 shear modulus and 1 Poisson ratio. This is due to the hypothesis of transversely isotropic that I try to show. But in case you don't have this behavior, you need 9 elastic constant, 3 Young modulus, 3 shear modulus, and 3 Poisson ratio. And the software enabled to take into account all the behavior of these materials.
In the software, or you develop a subroutine in this one?
The software is able to do, but we also have study and develop for different other application, a specific mechanical and numerical model, able to study the strength and beam. In fact, one of the first slides that I showed you was the mechanical modeling of a reinforced concrete beam with the possibility of reinforce the beam with the different layer in shear, in flexion, with different materials, with different orientation of the fiber. Of course, if you are interested, we can share this, and you can also improve if you desire our model.
So, one more question: have you tried two C channels like that instead of I-beam to see that to minimize the shear problem?
Yes, we are studying this very important possibility. Of course, the problem is remain the connection between the two channels. But I think that I continue to think that the best solution is to have a pultruded channel only in one sector without the second step that consists in the adhesive connection between the two elements. This is a still open field of research. Okay, I want to thank you again, everybody, Magnifico Rettore, and I hope to develop some of this research in collaboration with the professor of your architecture and engineering department. Thank you again.
Now our rector will present a small gift to Professor Luciano. So welcome to our rector.
They are civil engineers, I guess.
Yes, so some ideas.
Masters.